I hope this video isn't too interesting and ends up keeping you awake, though. If it does, at least you'll drift off with a few more facts in your mind than you had when you pressed play. It's the kind of problem I'm not entirely sure I should apologize for. Tonight, we're going to take a slow, starlit voyage through our galaxy, the Milky Way. But here's the question I'd like to begin with. If we can only ever see our home from the inside, how can we truly know what it looks like? The Milky Way is not just a backdrop to our lives. It is the very stage upon which all of human history, all of life, and every shimmering moment has played out. We live within its vast embrace, yet most of it remains invisible to our eyes, hidden behind clouds of cosmic dust and the sheer dizzying scale of space itself. In this journey, we will drift slowly from the familiar to the far-flung. We'll wander the spiral arms, linger among newborn stars, cross the quiet halo, and dip into the mysterious heart of the galaxy where a supermassive black hole resides. Along the way, we'll meet the many kinds of stars that call this galaxy home, the clusters they form, and the gas and dust that both obscures and creates them. We will explore not only what the Milky Way is made of, but also how we know what we know, the careful observations, the patient measurements, and the ingenuity that allow us to map something so impossibly large from our tiny vantage point. And perhaps we will think about what this galaxy means to us culturally, scientifically, and personally, as the only cosmic neighborhood we've ever known. So get comfortable, let your thoughts drift like starlight through the darkness, and join me as we begin our slow voyage through the Milky Way. If you could step far enough away from our galaxy, far, far beyond the pull of its stars, you would see it as a soft, glowing whirlpool hanging in the dark. From that impossible vantage point, the Milky Way would reveal itself as a vast barred spiral, a flattened disk of stars wrapped around a bright central bulge with long arms curling gracefully outward like the petals of a cosmic flower. It is a place of both order and chaos, where patterns emerge from countless random motions, and where light from billions of suns blends into a single pale shimmer. The scale of it is almost absurd. From end to end, the Milky Way stretches for roughly 100,000 light-years. A light-year is the distance light can travel in 1 year, about 9.12 trillion kilometers, which means the galaxy is wide enough that even at light speed, a trip from one side to the other would take longer than the entire history of human civilization by a factor so large it makes numbers feel slightly ridiculous. If our sun were the size of a single grain of sand, the galaxy would still be larger than the span of entire continents. Its shape is not simply a neat spiral drawn in space. At the heart lies a bar-shaped cluster of stars running through the central bulge. From the ends of that bar, the spiral arms unwind, rich with gas, dust, and newly formed stars. The main arms, Perseus, Scutum Centaurus, Norma, and Sagittarius Carina, sweep outward in gentle arcs. Between them lie shorter segments and spurs, like smaller branches in a great cosmic tree. From above, it would look like an artist's slow brushstroke through the night, spiraling ever outward. We rather modestly do not occupy one of the grand sweeping main arms. Instead, our solar system sits in a quieter neighborhood, a smaller spur of stars called the Orion Arm, or sometimes the Orion Spur. This spur lies between two larger arms, the Sagittarius Arm closer to the galactic center, and the Perseus Arm farther out toward the edge. Our location is, in many ways, rather fortunate. It is calm enough to avoid the more chaotic regions of intense star formation that might bathe worlds in harmful radiation, but close enough to the action that we're surrounded by a rich view of stellar life. From our position, we are roughly 27,000 light-years away from the galactic center. That might not sound too bad. After all, in everyday human terms, 27,000 of anything is not an unthinkable number. But in space, it is an immense gulf. If you could somehow travel at the speed of light, which you cannot unless you are light, it would still take you 27 millennia to get there. For comparison, 27,000 years ago, the last ice age was in full swing, and mammoths were still trudging across the Earth. This vastness also means that our nearest stellar neighbors are anything but next door. The closest star system to our Sun, Alpha Centauri, is more than 4 light-years away, around 40 trillion kilometers. Even with our fastest spacecraft, it would take tens of thousands of years to get there. In galactic terms, that is like saying the house next door is actually somewhere past the edge of the horizon, and to get there, you would need to walk for multiple human lifetimes without stopping. The Milky Way's disk is not perfectly flat. It has a gentle warp, as though the whole galaxy has been very slowly twisted over time. This warp is thought to be caused by gravitational interactions with neighboring satellite galaxies, smaller companions that orbit the Milky Way much as the Moon orbits Earth. The disk is also surprisingly thin compared to its width, like a cosmic pancake with a fluffy central mound. Most of the galaxy's stars, gas, and dust lie within a disk only a few thousand light-years thick, while a halo of old stars and dark matter surrounds it in all directions. This halo is the galaxy's ghostly outer boundary, and though it is far less dense than the disk, it holds important clues about the Milky Way's history. Within it are ancient globular clusters, spherical swarms of stars that have been orbiting the galaxy for billions of years, predating much of the structure we see today. The sheer number of stars in the galaxy is staggering. Estimates suggest there are at least 100 billion of them, and possibly as many as 400 billion. And yet the space between them is so vast that, on average, the nearest star to any given star is several light-years away. In a way, the Milky Way is more emptiness than substance, an enormous expanse in which islands of light float in oceans of darkness. From our small patch within the Orion Arm, we cannot see the Milky Way as an outsider would. Instead, we experience it from within, as a river of pale light stretching across the night sky. That light is not the glow of a single object, but the combined radiance of countless stars too distant to resolve individually, their light blending into a misty band. It is one of the few things in nature that is both an intimate part of our world and unimaginably far beyond it. Understanding the Milky Way's shape, size, and structure is like trying to sketch the floor plan of a house while standing inside a single room with no windows. We must piece together the whole from small glimpses, relying on careful measurement, the behavior of light, and the slow mapping of the sky. Every star's position, every swirl of gas, every faint whisper of radio waves tells us a little more about the home we live in. A home so vast that our entire civilization is a barely noticeable flicker within one of its countless stars. And yet, despite its size, the Milky Way is still just one galaxy among billions in the universe. From the outside, it might not seem particularly special, but from here inside it, it is everything. The stage, the scenery, and the quiet backdrop to our every moment. If you could see the Milky Way from far above, you would notice it does not form a perfect pinwheel of evenly curved arms. Instead, there is something striking at its center, a bright bar of stars cutting across the bulge from which the great spiral arms unfurl. This makes the Milky Way what astronomers call a barred spiral galaxy. The bar is not just a decorative feature. It is thought to act like a gravitational engine, channeling gas inward toward the center, feeding both new star formation and the activity around the supermassive black hole that resides there. The spiral arms themselves are not solid structures the way an actual whirlpool's currents might be. They are regions where stars and gas are more densely packed than in the surrounding space. But individual stars do not stay in the same arm forever. Instead, the arms are more like traffic jams on a cosmic scale. This density wave theory explains why the spiral arms are the cradles of so many young stars. As gas clouds drift into an arm, the added pressure from the denser environment causes them to collapse, igniting new stars. At the heart of the Milky Way lies a region unlike anywhere else in our galaxy, the galactic center. From our position in the Orion Arm, it is hidden behind vast curtains of dust and gas, invisible to our eyes even on the clearest night. Yet astronomers have peered through those curtains using infrared and radio waves, revealing a place of staggering density, ancient stars, and gravitational forces so extreme they defy everyday experience. The galactic center is dominated by a swollen bulge of stars, a dense, football-shaped concentration that extends thousands of light-years above and below the galactic plane. This bulge contains some of the oldest stars in the Milky Way, many of them low in heavy elements, which suggests they formed in the galaxy's earliest days. The sheer number of stars here is hard to grasp. Imagine the night sky. If every star you could see was suddenly packed into a space a fraction of its current size. From within the bulge, the sky would be so crowded with light that true darkness might be rare, the combined glow of millions of suns turning night into a perpetual dim twilight. But it is not just a stellar crowd. Nestled deep within this throng is perhaps the most intriguing resident of all, Sagittarius A, the supermassive black hole at the center of the Milky Way. Despite its immense mass, about 4 million times that of our Sun, Sagittarius A is surprisingly quiet most of the time, radiating only faintly compared to the raging, matter-devouring black holes at the centers of some other galaxies. We cannot see Sagittarius A directly because no light can escape its grasp, but its presence is revealed through its influence on the stars around it. One star in particular, called S2, has been a star of the show, so to speak. It swings in closer to Sagittarius A than Pluto is to our Sun, reaching speeds of thousands of kilometers per second. At those distances, the gravitational pull is so intense that the predictions of Einstein's general theory of relativity come into play. Gas and dust clouds swirl through the center, occasionally falling toward the black hole. When enough material gets close, it forms an accretion disk, a whirling maelstrom of gas spiraling inward, heating up to millions of degrees and emitting bursts of energy. Astronomers have also found evidence of massive outflows from the galactic center in the past, such as the Fermi bubbles. Enormous lobes of high-energy radiation extending tens of thousands of light-years above and below the disk, possibly caused by ancient eruptions from Sagittarius A. If you could stand safely on a stable platform close to Sagittarius A purely hypothetical notion since gravity there would tear apart anything solid, the sky would be unlike anything imaginable. Stars would whirl past in fast arcs, distorted by gravitational lensing into strange smears and loops of light. The Milky Way is not just a collection of stars, it is a vast, glittering archive of every kind of star nature has ever devised. From tiny, cool red dwarfs to enormous, short-lived supergiants, from the steady hum of main-sequence stars to the exotic remnants of dead suns, our galaxy contains a full cast of stellar characters, each with its own story. Astronomers often sort stars using the Hertzsprung-Russell diagram, a kind of map that plots them according to brightness and surface temperature. Most stars, including our Sun, fall along a band called the main sequence. The smallest and most common of these are the red dwarfs. They are so faint that none are visible to the naked eye from Earth. Yet they make up the overwhelming majority of the Milky Way's stellar population. A red dwarf's life is one of quiet efficiency. Because they burn their fuel slowly, they can shine for trillions of years, far longer than the current age of the universe. At the other end of the main sequence are the massive hot blue stars. These luminous giants are rare but impossible to miss. Their intense light can travel great distances, and they often dominate the regions around them. But their brilliance comes at a cost. They burn through their nuclear fuel at a furious rate, living only a few million years before running out and ending their lives in spectacular supernova explosions. When a star exhausts the hydrogen in its core, it begins to change. For stars like the Sun, this means swelling into a red giant, a cooler but much larger star whose outer layers expand dramatically. A red giant can be hundreds of times wider than the Sun, its surface glowing with a soft orange-red light. More massive stars follow a different path. When their hydrogen runs out, they move rapidly through a series of fusion stages, creating heavier and heavier elements until they reach iron, a dead end for energy production. At that point, the core collapses under its own gravity, triggering a supernova. The aftermath can leave behind either a neutron star, a city-sized object so dense that a teaspoon of its material would weigh billions of tons, or, for the most massive stars, a black hole. Among the most beautiful and mysterious places in the Milky Way are the stellar nurseries, vast clouds of gas and dust where new stars are quietly taking shape. These regions are not hurried. The process of creating a star can take millions of years, unfolding with a patience that only the cosmos can manage. Another striking example is the Eagle Nebula, made famous by the Hubble Space Telescope's image of the Pillars of Creation. These towering columns of gas and dust, each several light-years tall, are active sites of star formation. At their tips, small clumps of dense material called evaporating gaseous globules are collapsing under gravity, soon to ignite as newborn stars. Every type of star plays a role in the Milky Way's ecology. Massive stars seed the galaxy with heavy elements in their violent deaths, enriching the gas from which new stars and planets will form. Smaller stars preserve those elements over long timescales, acting as stable hosts for planetary systems. The constant cycle of birth, life, and death ensures that the galaxy remains a dynamic, evolving place rather than a static one. Perhaps the most humbling realization is that the stars we can see with the naked eye represent only a tiny fraction of those that exist. The vast majority, the countless red dwarfs scattered throughout the galaxy, shine too faintly for us to notice without a telescope. And yet, in sheer number, they dominate, forming the unseen backbone of the Milky Way's stellar population. They may not dazzle the eye, but their quiet endurance means they will still be here long after the last supergiant has burned out, their light continuing to fill the galaxy's night for trillions of years to come.